this video lecture, we will be solving this problem network delay time. We solved this problem in the previous video as well, but here we will be solving the same problem using another approach. I've attached the solution to this problem with the first approach, that is depth first search approach, in the description, so make sure to check it out before you watch this video. So in this problem, we're given a network of n nodes which are labeled from 1 to n, and we are also given a times array, which is basically a list of times as directed edges, that is each element in times is a tuple representing the starting node, ending node, and the time it takes to travel from the starting node to the ending node through the given directed edge. Fine. So we are also given a source node k, and we'll send a signal from that node, and we have to find the minimum time it takes for all the n nodes to receive the signal. It may be the case when it is impossible for all the n nodes to receive the signal. In that case, I'm going to return -1. So in the input we'll be given this times array and an integer k representing the source node, while in the output we have to return an integer representing the minimum time it takes to send the signal to all the nodes. So let's see the constraints. In the constraints, the length of the times array as well as the source may go up to 100, while the nodes are labeled from 1 to n, and the node's ui is never equal to vi, that is there is no self edge for any node, and the travel time lies in the range from 0 to 100. All the node pairs where exist a directed edge are unique. So let's better understand the problem statement using an example, as well as let's take a recap for the previous approach. So here we have the input test data. So this is the given graph that we have, or the network of nodes, and the source node is, let's say, k is equals to 2. So we are sending the signal from this node, and we want to find the minimum time for this signal to reach all the nodes of this network, and this integer which is present over the edge represents the time it takes to travel from the source node to the target node. So let's say we send the signal from this node, that is node number 2. Then it would take 1 second for the signal to reach this node, that is node number 1, and it will take 1 second for the signal to reach this node. So I will put 1 second for node number 1 and 1 second for node number 3. Then it will take 2 seconds to reach node number 4, and hence 1 plus 1 will give me 2. So 2 represents the number of seconds it takes for the signal to arrive at node number 4 starting from the node number 2. Fine. So this is how the signals will arrive at these nodes, and we can see that the minimum time it took to reach each of the 4 nodes is 2, because in 2 seconds I'm sure that every node has received the signal. Fine. So let's try to build the solution for this problem. So let's recap the previous solution that we discussed for this particular problem. In that solution, we used depth first search, or DFS algorithm, which is a standard and simple traversal algorithm for graphs and trees. I simply started DFS from my source node, and I kept a auxiliary array where each element for that auxiliary array, let's say k, gives me the minimum time for the signal to arrive at that node. Fine. And then I performed my depth first search from this source node and kept on updating the values in that array. So whenever I reached a particular node along a path such that the time it took along that path is smaller than the time which we already have for that node, in that case we updated the timing for that node. So in short, we explored multiple paths to arrive at each node using depth first search, and out of all those paths we took that path which gives me minimum time for the signal to arrive at that node. Fine. So if you want to have a deeper look for the solution, then I would suggest you to go to the previous video for this problem, and I have attached the link for that video in the description, so make sure to check it out to better understand the solution that we'll be discussing here. Fine. Okay, so let's discuss the second approach to solve this problem, that is BFS approach. Since we can solve this problem using depth first search, BFS can also be used because all we want is to explore is for each node we want to explore all the path. That means I want to arrive at a given node along all the paths, and we want to find the shortest path or the path along which the signal reaches with the minimum cost or time. So the BFS simulation is simple. Let's say for this particular node, here I'm assuming that you have basic idea for BFS algorithm. So the source node is this node. I'm starting from here. That is, the signal starts from this node, and let's say we have this queue. So start from this source node, we push it into the queue. Okay, so let's simulate the BFS algorithm for this particular test data. So initially we push our source node into the queue, that is k, and this is my signal received at array, which basically gives me the minimum time for the signal to arrive at a particular node. Let's say I want to arrive at node number k, then this array will give me the minimum time to arrive at node. So initially we have this node into our queue, and the time for this node is 0. Fine. Then I pop this node out of the queue. So this is popped out, it is removed from the queue. Then I will move to the adjacent nodes, that is this node B and node A. And I can see that the time it takes to reach node A from node K is 6 units. So initially it is infinity, that is the array signal received at is initialized with very large number. Let's call it infinity. So here we had infinity initially in this array, or a very large number. So in C++ we have int max for that. Then I can see that 6 is the time which the signal took from K to A, to move from K to A, and we can see that 6 is less than infinity. So I will update my answer for the node A to 6. So this is updated to 6. Then I will move to and I will push this node into my queue. So now I have A into my queue. Then I will move to another adjacent node, that is this node number B, and I will see the time which the signal took to move from K to B, and the time is 5 units. So I will update the timing for this particular node to 5, because initially it was infinity and 5 is less than infinity. And I will push this node into the queue. So it is pushed into the queue. Then I will pull my front node from the queue, that is this node number A, and I will traverse the adjacent nodes for this node A. And we have only one adjacent node for this node, that is this node B, because we have a direct edge from node A to node B. So the time it took to move from A to B via this path will be 6 plus 2, that is 8. So can we update the value for node B to 8? And the answer is no, because 8 is greater than the already existing time that we have for this node, which is 5. So we're not gonna update that. Fine. Then I will remove this node B from the queue, and I will traverse the adjacent edges for this node B, and we have only one such edge, that is this one. And I will update the value for node A to 5, which is the value for this node B, plus 3, that is 8. So should I update the value for node A to 8? And the answer is no, because the already existing value is 6. Fine. So it is of no use to update the value for node number A. Here my BFS ends because I have explored all the nodes of this graph. And finally I have my signals received at array prepared, which contains the value for each node. So the signal arrived at node K at time 0, and it arrived at node A at time 6 units, while it arrived at node B at time 5 units. Fine. So that's how the BFS algorithm is working. Let's try to implement the solution. So what will be the answer for this particular test case? The answer would be 6, because this is the largest integer in this array, and in 6 seconds or 6 units, I'm sure that every node in this graph has received the signal which I emitted from the node K. Fine. So that's how this BFS algorithm is working for this particular problem. Let's see the implementation for this solution. Here we have the implementation for the approach that we discussed in the previous slide. So this is the adjacency list that we will be using to store our graph. This is the function network delay time, which takes in the times array, the size of the times array, and the source node. We traverse over the times array, and I will prepare my adjacency list, which I declared here. And in the adjacency list, it is basically a directed graph, so I'm pushing a one-way edge from source to destination, while this first integer represents the time which we take to move from source to destination. Then I declare my signals received array and initialize it with a very large value, that is, no node has received any signal yet. Then I will call my BFS function while passing in this array and the source node. So let's see the working of this BFS algorithm in the next slide. So here we have our BFS function, which takes in the signal received array and the source node. It declares a queue and push the source node into the queue and initialize the signal received array for that node with 0, because at node number k we are just starting, that is, the signal is being started. Initialize that node with 0. Then I'm iterating over the queue. While the queue is not empty, I'm pulling the front node from the queue, then I'm popping that node from the queue, and then I'm iterating over the adjacent nodes of that queue. And for the adjacent nodes, I have three factors. The first factor is the time, that is h.first. So it is the travel time to move from the current node to that particular neighbor node. And the second integer in the pair represents the target node where we are reaching. Then we have my arrival time, which is the time to reach this current node here, plus the time which we take to move from this current node to the neighbor node, that is this time. So that's the arrival time for that particular neighbor node. Then I will check if the arrival time for that particular node is smaller than the already existing arrival time for that neighbor node in my signal received array. If it is the case, then there is a scope of improvement for the arrival time, and hence I reinitialize my signal received array at that neighbor node, and I push the neighbor node into the queue for further processing the adjacent nodes. Fine. After I have executed this function, I will have my signal received at array prepared for all nodes. Then I will initialize an answer variable to a very small value, and I will iterate over the signal received array, and I will find the maximum integer in that array. And if the answer is int max, that means here what I'm checking is if the answer is equals to the very large value to which we initialized our signal received array initially here, that means there is at least one node which has not been updated, or the signal hasn't arrived at that node. In that case, I'm returning -1, otherwise I'm returning answer. Fine. So that's how this BFS algorithm is working for this problem. Let's see the code implementation for this solution. So this is my solution class. We have this adjacency list as the graph or the network. Then we have our BFS function, which takes in the signal received at array and the source node. This is my network delay time function, which takes in the times array, the size of the times array, and the source node. So initially, first of all, I build my adjacency list and prepare the network in my adjacency list, which I declared here. Then I declare my signal received at array and initialize it to a very large value. Then I call my BFS function while passing in this signal received at array and the source node. After this BFS function has been executed, I will have my signal received at array prepared for each node, and I will initialize my answer to a very small value, and I will iterate over the signal received at array and update my answer variable to the maximum integer present in that array, which represents the minimum time it took for the signal to spread in that network. Then I check if the answer is equal to int max. That means if the answer contains a very large value, that means there is at least one node which is unreachable, then I'm returning -1, otherwise I'll return answer variable right from here. Let's see the working of the BFS algorithm. So in the BFS, I declare a queue and I push the source node into the queue. Then I initialize the signal received at array for that particular source node to 0. Then I iterate till the queue is not empty. I pull my top node from the queue. I pop that node and I traverse the adjacent edges for that current node. And for every edge, I have three factors. That is the time to move from the current node to the neighbor node itself, and the arrival time, which is calculated by adding the arrival time for the current node plus the time which we take to move from the current node to the neighbor node, that is this time. Then I will check if the arrival time that I computed here is smaller than the arrival time that I already have for the neighbor node. Then I will update the arrival time in my signal received at array to the new value, and I will push that neighbor node into the queue for further processing. So that's how this BFS function is working, and this is the implementation in C++. Let's see the implementation in other languages. So this is the implementation in Java, and this is the implementation in Python language. So that's all for this video. If you like the video, then hit the like button and make sure to subscribe to my YouTube channel and give your feedback in the comments below. I've attached the first part of this video in the description below, where I explained the depth first search approach for this problem. So make sure to check it out to better understand the idea which I explained here. I will see you in the next video. Till then, stay tuned with me.